Hello, space fans. Welcome to another live broadcast. I'm your host, Scott Lewis, and with me again is the magnificent Astro Katie, Katie Mack. How you doing, Katie?
Hello, I'm good. How are you doing?
I am enjoying a cool night here in Los Angeles. How is tomorrow evening in Melbourne, Australia?
It's very nice. We've had a beautiful, warm day, and I've spent it all inside. But it's unseasonably warm for autumn at the moment.
So, like, how warm is it down there?
I don't know, like room temperature.
Well, that's not too bad. It's been going back and forth out here. But we're talking about things today that are much hotter than our ambient temperature that's been outside. We are talking about stellar deaths and supernovae and awesome exploding stars. So before we get started, I want to let everybody know how you can get in touch with us. I have the Q&A app enabled for that you can get here on YouTube, also on Google Plus in our event page on Space Fan News. You can also tweet at us. So I am Scientific Scott down here, and Katie, I believe you have your Twitter handle up. Katie is Astro Katie. So if you would like, you can send us tweets, but the best way, honestly, because I have Twitter up, but it's going to be really distracting, but I will try to catch them all. But using the Q&A app and YouTube comments are going to be the easiest way for me to find them, and we'll try to answer them live on air if possible. If not, we will do follow-ups, because we do have a secret at the very end of the show, so stay tuned for the end for our cool announcement of sorts. So stars, they die. They take a long time to die. So what do we know about stellar deaths, and what can we learn from them? So tell me about some stellar deaths.
Okay, so the way a star has a lifetime like anything else, and the way that a star dies depends on how massive it was to begin with and what happens during its life. And so there are a few different ways to explode a star. I'll talk about the different ways to do that. So the thing about supernovae, though, which a supernova is just a star explosion. The thing about supernovae is that they're super useful in astronomy because they're extremely bright, and so a supernova can outshine the entire galaxy that it lives in for a few days, and so that. Or I mean, up to like 100 days, depending. So that supernova can be used to see really, really distant objects, and with certain kinds of supernovae, we can learn about the distances in the universe by knowing how bright the supernova should be and how bright it looks to us. That can tell us something about how the universe is expanding and what the distances are and stuff like that. So
like one event is able to outshine billions of stars. And that's kind of crazy to think about for a second. Like one little event, or one
star blowing up. So a star blowing up can be extremely bright. And so there are a number of different ways that we use supernovae. And okay, so it depends on what kind of supernova, which depends on the mass of the star. So I'll give you sort of a rundown on these. So one of the so basically everything about a star depends on how much mass is in it and like the chemistry of the cloud that it grew out of. Right. So for sort of ordinary stars that are growing today, if you have a low mass star like our sun is a low mass star. If you have something that's less than like 8 times the mass of the sun, it's actually not going to blow up. It will not make a supernova. It'll do some interesting things, and I'll tell you what it'll do, but it's not going to go boom, which is a little disappointing, but probably good for us, seeing as we're really nearby.
Yeah, I could say so, but still, I mean, we always hear about supernovas, those are awesome, and our stars are like, nah, I'm on a diet, and so I'm not going to be massive enough for that to happen.
Yeah, it's just going to kind of peter out eventually. I mean, it'll get puffy and it'll blow things out and stuff, but it won't go supernova. But if you're more massive than Sun, with something like 8 solar masses to like 15-ish, then you can explode in what's called a core collapse supernova, which is a really awesome dramatic thing. And if you're like super really massive, you can do something entirely different called a pair instability supernova, and I'll tell you about that also. But that's really rare.
Super massive.
Yeah. So the core collapse supernova is kind of what you might sort of think about if you have a vague understanding of how supernovae happen. So basically, a star is an object that's held up by the nuclear reactions going on inside. So it's creating heat and it's creating pressure inside the core of the star by the fact that nuclear reactions are happening. So, or you start with a star that's mostly hydrogen, and the hydrogens come together and they form helium, and that puts out energy, and so you have this sort of energy source at the heart of the star, at the core of the star, and that's putting out energy that keeps the star puffed up, and then the gravity of the star is pulling it together, and so there's this balance between the outward pressure of the fusion reactions and the inward pressure of gravity, and that's it's called hydrostatic equilibrium, if you want a fancy name for it.
Fancy name.
But it's just this force balance, right? And so as long as you have something inside that you can fuse into something else and create energy with that, you can keep the star puffy, and you can keep it holding up against gravity. But as the star is growing, or as the star is evolving over time, it's taking all the hydrogen, it's fusing it to helium. You're running out of hydrogen, then you start taking the helium and you start fusing it to the next elements up, and you keep going up and up the elemental chain, the periodic table.
Right.
And as you do that, you're running out of the lighter elements, sort of in layers in the star, and you're ending up with heavier elements. And
so just to slow down for a second. So we're taking hydrogen, and they're being fused, and it's forming deuterium and then helium. So you have these heavier elements, and so it means we're running out of hydrogen. It's not like they're leaving, it's just the fact that it's being turned into heavier elements, and those are
in the core,
something else in the core. So as that's happening, there's less atoms, they're just heavier. Does the core of that star change at all, or what's going on the inside now that we know that there's heavier stuff going on?
So basically you end up with a sort of layered thing where the farther into the star you get, the heavier elements you're forming, and as you go out you have more of the lighter elements, because the fusion is happening more in the center and kind of in layers as you go out. And I think you have a picture of this hanging around somewhere, or we were looking at these earlier.
Yeah, I'm trying to pull that back up, close that tab down.
Sorry. So you get this sort of like onion layer structure in the star, where you have heavier elements at the center and lighter elements as you go out. And you can keep forming heavier elements for a while, but at some point you end up with a situation where if you keep going, you would actually lose energy, or you would take more energy than you have to do this fusion. So if you're fusing 2 hydrogen atoms into helium, you actually get energy out of that. So the energy that you get out is more than what you put in from that reaction, and so you can use that to create pressure, to create radiation, and all of that. And that keeps going until you get to iron. And once you get to iron, if you try to fuse iron into heavier things, it takes you need energy. You need to put energy in to do that. So here you have the onion layer thing. And so once you get the core has iron in it, that iron can't be fused into anything heavier or without putting energy into the thing. So trying to fuse iron into something else will not give you any energy, will not give you any pressure, and you can't hold up against the gravity. And so you end up in this situation where you've fused a bunch of elements together, and you have this core that's pure iron, and there's nothing to hold it up against gravity. And just a big sphere of iron with that much gravity on top of it is not strong enough to stay together. It's not strong enough to keep from collapsing. So you get to this point where you have this iron core in the star, and it's being pushed together by all the gravity of everything around it and by its own gravity, and it starts to collapse. And this is when things get really trippy. So the iron starts to collapse.
Turn on the Pink Floyd, guys. We're gonna go for a ride.
Yeah. So you get so much pressure that the protons and electrons start to fuse, and you make neutrons, and you end up with sort of converting this sort of ball of iron into one giant nucleus made entirely of neutrons, or almost entirely of neutrons. And then and neutrinos are escaping, and this thing is collapsing. Let me out of here!
There's so much iron, not a big nucleus. That's
right. Yeah, thanks.
Yeah, no, I had to answer more by them. They're escaping, right?
Yeah, they're escaping. Yeah, so it turns out when you fuse a proton and electron, a neutrino comes out. So you're creating this like nuclear ball of neutrons, and that's like shrinking. And when that happens, that's creating this crazy nuclear matter, and the outer layers start to fall in, and the thing kind of bounces. It kind of rebounds, and it creates this shock wave that goes through the outer layers of the star. And mind you, it still looks like a star on the outside, right? It's just before that all this stuff is happening. Mm-hmm. But then you make this shock wave, and this shock wave is so powerful that it completely blows up the whole rest of the star. So then you have this situation where you've got this massive explosion throughout the entire rest of the star, and at the center you've got this core of nuclear material, and that core becomes what's called a neutron star, which is like this extremely dense object made of mostly sort of neutrons.
And we were discussing this beforehand about. Yeah. It's funny because if you were following us on Twitter, we were being kind of silly about it, but we were trying to find out what a teaspoon, or I think we came down to like a sugar cube amount of neutron star. No, it was white star was the
white dwarf stars and neutron stars.
Right.
Yeah.
So a white dwarf star material in the form of a sugar cube would weigh the same amount as a Mack truck.
Sort of, yeah, like a semi-truck, or I think we found out it was, or a white dwarf material, a teaspoon of white dwarf material would also be as much as 6 great white sharks.
Yeah, it's like 6.5 great whites. So we narrowed it down between a blue whale and a great white shark.
Yeah,
that, okay, somewhere along those, that's where this tiny amount of white dwarf material is.
Yeah,
or as opposed to, go ahead.
Yeah. The white dwarf star, the teaspoon of it weighs about 15 tons. But the neutron star, which is what I'm talking about right now, a teaspoon of that weighs about 4 billion tons.
Oh, is that all?
Yeah.
4 billion, okay.
We worked out that's about as much as Everest, right?
No, it was 900 Great Pyramids. 900 Great Pyramids.
Yeah, but I think that was about as much as Everest.
Yeah.
Anyway, so neutron stars, extremely dense. Okay.
I mean, nothing against you, neutron stars. We're not saying that you're not smart, but you're really dense.
Really dense, yeah. Yeah. So like a neutron star that's about the mass of our sun, would be about the size of Manhattan. So really quite small.
I would not want to go to Broadway though, because that'd be kind of a downer. Like literally, like just the gravity alone, I would be crushed.
You would be, yeah.
But this isn't the only type of supernova that happens.
This isn't the only type of supernova. Okay, so this is the kind of supernova that makes neutron stars, and we can talk about neutron stars in a little bit.
Yes.
So those make neutron stars. The other thing about type 2, so this is called a type 2 supernova, or a core collapse supernova. The other thing about type 2 supernova is because those neutrinos are escaping, in principle, if it's close enough, we can detect those neutrinos. And we did that once with a supernova called 1987A, where we have a neutrino detector called Super Kamiokande. At the time, it was just Kamiokande. It was not super yet. It got upgraded. And this neutrino detector...
That's quite the upgrade, though. Like, you have to explode to be upgraded, just so you know.
No, it was they made it better. So in this neutrino detector, we saw like, I don't know, a dozen neutrinos that came out from the same part of the sky and at the right time to have come from the supernova. But the really cool thing about it is that the neutrinos get to you before the light does. So when a supernova goes off, you see, a bright flash of light that outshines the galaxy, but the neutrinos get there before the light. And it's not that they're traveling faster than light. They're not superluminal. They're not traveling faster than light. The reason that the neutrinos get there first is because the light gets trapped. So as this explosion is happening, all this light is produced from this explosion of the core, but it gets it starts bouncing around in the layers of the star. And
very similar to how the light we get from our own star takes a long time to actually escape the star itself. It only takes 8 minutes, 20 seconds to pass the distance, but to actually leave the core where that light's being created, it takes hundreds of thousands of years for it to actually escape that.
Yeah, so there are different estimates for exactly how long that takes, but it's like a really long time between the core and the outer layers of the sun. And similarly, with a supernova, it doesn't take that long, but it does take some time for the light to get through all these layers. And so, but the neutrinos don't care. Neutrinos hardly interact with
anything. Neutrinos are the honey badgers of the universe.
Yeah.
Like, we don't care.
Neutrinos don't care. Yeah. So the neutrinos can stream right through this train wreck of a stellar remnant, and the neutrinos have a head start, basically. And so they arrive a little while before the light, and it's like a few minutes, I think, for that supernova between the neutrinos and when we saw the actual light. So that's kind of cool. So that's one way that the type 2 supernovae are really fun to work with. But that's not the only type of supernova. The type that cosmologists care about mostly are called type 1a, and those are basically a white dwarf star goes through a thermonuclear explosion and blows up completely. So I mentioned white dwarfs. A white dwarf star is a really compact star that's the end state of a star like our sun. So our sun, over time, it will puff out a little bit. It'll become a red giant. It'll puff out a lot. It'll engulf the orbit of Venus. It'll get out to where we are. It'll burn off the oceans, and then it'll throw off the outer layers and make what's called a planetary nebula.
Right.
A very beautiful object, which is like the outer layers of a star having been blown off. And then the inner core of our sun will be this sort of burning white ember called a white dwarf. And a white dwarf star is no longer going through fusion. It's just sort of sitting there. It's made of carbon and oxygen, and it's held up by what's called electron degeneracy pressure, which is a kind of different kind of pressure that doesn't have to do with fusion.
Mm-hmm.
So a white dwarf star is this kind of sort of inert star that's just very hot, very dense, glowing thing held up by degeneracy pressure. And over time, white dwarf stars cool, and then you get like called a black dwarf star eventually, where it runs out of energy and it just cools down, and it becomes this kind of lump of carbon, oxygen, coal, basically. So white dwarf is what our star will be, and it'll be kind of boring after a while because it'll just sort of passively cool. But if our star had a companion star, then it could, in principle, become a type 2 supernova. And the way that works is that you have a white dwarf star and you have a companion star, and the white dwarf, the white dwarf has whatever the companion star is. They're orbiting close enough that the white dwarf is pulling material off of the companion. So usually we think about it as like, a red giant or something like that orbiting a white dwarf star, and the white dwarf is pulling material off of the red giant. But it's possible that you have two white dwarfs orbiting each other, and then they come together in some way. And so what happens is, if you get too much material onto that white dwarf, if the white dwarf gets too massive, then it can't hold itself up anymore. The electron degeneracy pressure can't hold itself up. And then the white dwarf undergoes a massive star-wide thermonuclear explosion. So the whole thing becomes this massive nuclear bomb, and it just completely disrupts.
So like
it blows itself to pieces.
A white dwarf hug is like the worst hug ever, is what you're saying. If they like, oh, come here, and like the biggest explosion that we know of right now.
Yeah, that would be bad. Yeah. And you don't want to be the companion star. I mean, this is the thing. Like,
I don't think you want to be either at that case. I mean,
they talk about the companion star, right? For a companion star of a white dwarf, or sometimes like if a neutron star has a companion star, like there's this companion star, but the companion star is always being eaten, right? Like it's always this really dysfunctional relationship where the companion star is like being swallowed up layer by layer by the dense star that it's orbiting with.
And we've all had those friends, like, oh, let me come hang out with you and mooch off you for a while. Oh, I'm done. Explosion. Yeah.
Yeah. So it's actually unclear at the moment if type 2 supernovae are always like a double degenerate scenario where it's two white dwarfs, or if it's a single degenerate where one is the degenerate white dwarf star and the other one is this massive red giant or whatever. It's unclear which of those scenarios happens how often. So there's some evidence that maybe the double degenerate, the two white dwarf stars, is much more common, or all the time even maybe. But we've looked for the X companion star in the aftermath of these type 2 supernovae, type 1a supernovae, and we've maybe had hints of an X companion star, but it's kind of unclear. So we're still not sure exactly how this happens, but we know that it's a white dwarf going kablooey. And so the reason that those are...
I've got an image that I'm going to share real quick of that, because they're just amazing. Here we go. Right here. This is the remnant of that happening. I mean, okay, so I'm going to zoom and enhance, because this is a 12 megabyte file that I just got. I've been waiting for it. But just looking at the structure going on here, I mean, it's beautiful. This is the result of that terrible hug. So even if it is a bad time, it's beautiful at the end of the day.
It is beautiful, yeah.
Just not if you are the hugger or the huggee at that point.
Right.
And I think now, I'm totally going to call type 1a supernova white dwarf hugs. They're just really bad.
All right. So the reason that they're useful for cosmology is that we think we have a good idea of like how bright a white dwarf exploding should be, because they always explode when they get past this critical mass, the Chandrasekhar mass, which is the most mass a white dwarf can have. And so we have an idea of how bright they should be, and then we look at type 1a supernovae in other parts of the universe, and we see how bright they look, and then we can kind of figure out how far away they ought to be. And that lets us sort of measure the distances to other objects, to other galaxies. So those are the sort of most important, I guess, types of supernovae. The type 2, which is the core collapse, which is the one where you get the neutron star.
Right. And I've got an image of one here.
Type 1a. I should also say, with the type 2, you could also get a black hole if the star is massive enough. Instead of a neutron star, it might turn into a black hole. So this is a cool picture. This is the Crab Nebula, which is the result of a type 2 supernova. And it has a neutron star in the center.
It's like right here is where it's at.
Yeah, and it's a pulsar. So that neutron star has a magnetic field, and it's putting out a jet, and that jet like points at us sometimes 30 times a second. It's
30 hertz.
Yeah, and it's super cool. So we see neutron stars sometimes at the centers of these supernova remnants.
And I made a GIF of this from a really cool animation, but this is the center of the Crab Nebula there, M1, being looked at in both X-ray light on the left and optical, so with Hubble. And
so cool.
I love this. So this is the pulsar that we're talking about, and it's causing because it's also called what, a pulsar wind nebula.
Yeah. So the stuff around it is this material that's been ejected from the pulsar, and like the layers of the star that's been pushed out, and so the pulsar is spinning really rapidly, and it's got this magnetic field that's all tangled up, and it makes sort of waves in this material, and you see those waves propagating out in like real time. I mean, those images are from like a few years apart each, I think, right? But
right, yeah.
It goes, yeah. So you can actually see things moving because these neutron stars are so dense and massive, and they're they got this magnetic field, and so doing this really cool stuff to the stuff around them. So we're like almost out of time.
We are, but there are some questions, so let's try to hit those real quick.
Let's get some questions. Yeah.
Because there's just so much, and we'll also talk about our big secret. We kind of just hinted at it right now, but we'll get to it. Let me see here. I don't really know if we have a good answer for this, but I'll ask you, and you can let us know if this is even a good question for it. But hi, people. Do we know? This is from Kurt Lurcher. Do we know how big is the amount of antimatter blown out in a supernova?
So when the supernova is happening, so you're blowing up all the layers of stuff. The star itself is mostly made of matter. But so some of the neutrinos are like antineutrinos that you get out of it, I think, and so that's antimatter. But mostly it's just matter. You're just blowing stuff up. However, there is a type of supernova called a pair instability supernova, where if a star is really massive, like more than 150 times the mass of the sun, then it can go supernova because you get so much energy being produced inside that gamma rays are turning into pairs of positrons and electrons. So you get a matter-antimatter pair. So you can have so much energy in these gamma rays that they can make matter-antimatter pairs, and then those can't hold up the star, and so you lose the pressure support, and you can get a situation where the whole star blows itself to bits completely, and that's a pair instability supernova. So that's kind of driven by antimatter creation. So that's kind of cool. And also pulsars, when they're pulsars have these jets coming out, accelerated by the magnetic fields, and pulsars can put out positrons in their jets as well. Along with electrons, so pulsars can make electron-positron pairs and have those shoot out also. So, but the supernova itself, most of what the supernova makes is not really antimatter, but like heavy elements. So, we had this onion layer kind of thing where you're fusing all the elements in the star. At some point, you can't fuse things heavier than iron, but because you'd have to put energy in. But when the supernova explodes, that has so much energy that can fuse the heavier elements. And so most of the elements that we get that are like the heavy elements that are in the Earth and stuff come from supernovae. So come from that, very energetic explosion. That's where you get like the heavier things. So gold and uranium or whatever.
Right.
Those kinds of things are coming from these extremely energetic explosions because you need that extra energy to make these heavier elements.
So and I think that's a good thing to really keep in mind too, is that we know we have heavier elements than iron on this planet. Right now I'm using a computer that has things that are heavier than iron. So we know that the solar nebula, everything that formed us, had to have had a previous death of a star to bring those elements into what made our solar system. So we're not just talking about one cycle of a star forming, but there had to have been another star formation and a huge exploding death to create this awesomeness.
We know there have to have been several generations of previous stars to get enough. We call them metals. Anything that's heavier than helium, basically, in astronomy, we call it a metal, even though it's not necessarily. Thanks. So in order to get all these metals, in order to, as they say, pollute the interstellar or intergalactic medium with all these heavier elements, you need supernovae. You need a lot of them. So We know that our star is not a first generation star, and it's not a second generation star. It's farther along. So we are all made of not just star dust, but like star ash, like star innards. We're made of like.
We are the results of a scattered urn of.
Yeah. Yeah, we're star carnage basically. So we're the result of these extremely energetic, dramatic, explosions of previous stars.
Nice. So I'm going to pull up one more because there are some that actually going to touch on some other things that we're doing. But let's see here. From Mack 58R says, if you get a chance, take us through what a star like Betelgeuse or Betelgeuse would look like before it goes boom. What would be the first clues or changes that would be like, whoa, that's important?
Well, so Betelgeuse actually could go any minute. Like, we already know that it's at the end of its life, and it's like pulsating a little bit. It's like looking kind of unstable. So Betelgeuse is a red giant star. It's really, really big. I don't know what kind of supernova it's gonna do, but I know it's close. So I think that, let's see, it's a red giant, so it's gonna do some kind of core collapse, I guess. It's a massive star, and so it will go boom. It's not close enough to hurt us, so when it does go boom, we'll be okay. But we should be able to see it, and it should be really exciting. But yeah, we already know that it's almost there. So it could go any time between now and like 10 or 100,000 years from now, something like that. So really soon. Astronomically speaking, it's just about to go off.
So astronomically speaking,
any century now.
Any century now. Okay.
Yeah.
So hold on to your cyborg arms, because you might, it could be a while, but on our scale. But we live tiny, in so small lives compared to the universe.
Yeah.
Well, there are some other questions here. Maybe we can answer them afterwards, or maybe follow up on Twitter. But Katie, first of all, thank you again for coming back. This is our third show, and we're doing more and more. I love them. We will be, our big surprise is that we are making a video right now. We are almost done with the majority of the footage, just putting together some audio on it, and should be released either tomorrow or on Sunday. So stay tuned for that. That will be here on Space Fan News Channel. So if you're, are you looking forward to that and more awesome things like this, make sure to subscribe down there, I think, or down there, depends on what we're looking at. Katie, where can people find more about you?
Well, you can find me on Twitter at AstroKatie. You can also find me on Facebook at facebook.com/AstroKatie. I'm on Google Plus at +KatieMack. And you can go on my website, astrokatie.com, and you can see stuff that I've written and things like that. Mostly Twitter. I'm mostly hanging out on Twitter. That's a good place to look for me.
You got a lot of tweets. I've got to catch up.
Yeah.
I've got to catch up. So again, I'm Scott. You can follow me down at Scientific Scott on Twitter, plus Scott Lewis on Google Plus, and this is Space Fan News. We are just over 2.1 million followers on Google Plus, so you guys are all awesome. Thank you for allowing us to have these great conversations. We're going to be releasing more straight YouTube videos coming up here soon. And I know a lot of you guys were asking about Tony. Tony has been doing something super secret. It will be released next week on our sister channel, Deep Astronomy. So look forward to that. It's going to be awesome. I was talking about him with it earlier today. It's going to be great. So look forward to that. Again, thank you guys all for watching. Give us a thumbs up and keep looking up, guys. See you guys next time.
Bye. Thanks.